Hello, everyone. I'm Ron Swartzentruber, Director of Engineering, responsible for optical fabric products for Lightelligence. Pleasure to be with you today. And we're going to talk about the advantage of using Optical CXL for disaggregated compute architectures. It's been a great day so far with all of the presentations. And now we'll take it a step further and talk about connectivity. So we're looking here at a memory-centric shift in the data center. We'll look at the growth of large language models and why is optical CXL technology needed. And then we're going to show you a case study. So at Lightelligence, we needed to prove to ourselves that this optical technology was valuable. So we ourselves did built up an application to do a demonstration, and we'll talk about that in this presentation. So first off, disaggregation. What you can see is with composable data centers, you can see that the compute is no longer the dominant resource in the data center. It's memory and access to memory. Memory bandwidth has become the dominant criteria for how the data center is being designed. These applications can now run and define the machines that they run on, which is an additional degree of freedom that the traditional data center did not have. So we are seeing this shift. There's a lot of effort going on into how to create these disaggregated data centers, but we believe that optical CXL will be needed. I think you've all seen these charts of just the AI trends. The models are getting larger and the need for memory bandwidth continues to grow. CXL, and specifically CXL memory listed in the chart on the right, is well poised to meet the latency requirements of these applications. And so what you can see is that roughly, a NUMA hop away, the CXL memory is perfect for some of these applications, as compared to, you can see disaggregated memory, SSD or hard disk, in microseconds away. It just doesn't scale. So add this to the mix is that optical interconnects will give you an additional reach. So your cold storage or your warm storage, you may put that further away, and so the optical connectivity gives you the ability to connect to those memories that are further away, and optical CXL allows them to be low latency. So this chart really compares CXL with Ethernet. So RDMA is the dominant remote memory protocol used today in the data center. But the problem with RDMA is that there's a huge latency penalty involved. And you can see hundreds of microseconds just because, Ethernet is latency tolerant. It's not sensitive to latency versus CXL is very latency sensitive. So that gives CXL a dramatic advantage there. I think you've all seen this, over 250 member companies supporting CXL. The big advantage is that CXL added the memory and cache coherency functions to PCIe, which is ubiquitous today. So a lot of the infrastructure still can be maintained. Our products work with both PCIe and CXL, but with the addition of the CXL supported processors, the switches such as the XCON switch, and also the CXL memories. There's several companies listed here, Samsung, Micron, and others that have the CXL supported memories. So why optical CXL? So the signal loss in copper is extremely high, as you can see on the left chart, right? So as you span distance, the copper loss is extremely high. You can only, maybe drive a Gen 5 cable, maybe 2 meters, right? So it becomes very difficult, even within the same rack, to start using copper at these high speeds. The latency we've already talked about, but most Ethernet copper solutions use FEC. PCIe does not, but you can see the difference when you're comparing that to optics. And then the cable cross-sectional area. So just extremely smaller. You can put multiple wavelengths in a single fiber and support a much smaller cross-sectional area using optics. If you've ever looked inside today's servers, you have the bulky MCIO cables, etc. Optics gives you the ability to remove that. So simply put, our product will extend the reach of the CXL fabric, allowing applications to run across multiple racks and extend the reach of the CXL interconnect, allowing you to break through the rack. So in these composable data centers, you may have some of these older generation memories in a rack on the other side of the data center that you want to use. Or you may just simply, for power reasons, they need to be on a separate power supply, or for cooling reasons, the memories need to be in a separate chassis as compared to the compute. So there's all kinds of reasons forcing data center architects to disaggregate the memory, but optical CXL gives you the ability to connect them. Okay, so let's talk about the case study a little bit. So we provided this demonstration at the Flash Memory Summit last August. We won a Best of Show for this demonstration. And what we were doing was a large language model inference. So on the left, you can see a Supermicro server. On that server was an AMD Genoa. It's a CXL capable CPU. Also is installed the MemoryVerge memory tiering and pooling software. We used an NVIDIA A10 GPU to run the inference. And we connected PCI Gen 5 slot. So what you can see here is a Gen 5 by 16 PCI slot with the Photowave card supporting 2 CXL links, okay, with sidebands. Connected to another Photowave card in what we called our memory expansion module. So this was a purpose-built piece of hardware for the demonstration where we could connect to 2 CXL memory expanders using an FPGA. So this was the demo setup. Now let me talk a little bit about the model that we used. So we used OPT66B, which is perfectly sized to fit inside a single 128 gigabyte memory expander. Our demo was very throughput intensive, so we wanted to use news text summarization, and OPT66B worked well for us. Here you can see some of the results as the inference was run. And I'll just call your attention to the ones that matter is the decode throughput. So in terms of tokens per second, the CXL memory was running, I should say we compared running the large language model on the CXL memory versus running it, the CXL memory, which is connected over the optical link, versus running the model on the solid state drive in the server itself. So we compared those two, and you can see on this chart the decode throughput just running on disk was close to 2 tokens per second versus the CXL memory was 4.8. So about 2.5 times better decode throughput using the CXL memory. And looking at the latency, the latency was about 1/3 using the CXL memory. So a huge advantage there, even despite the fact that the memory was disaggregated and roughly 10 meters of fiber away from the server itself. This was the GUI output. So as I said, it's news text summarization. You take the file text input of news that comes across the wire, and the AI model summarizes it into just a few sentences. So that's what the model was working on. Here is a sort of a real live chart as the model was run. You can see it takes roughly 400 seconds to do the inference. And some things to note was that the GPU utilization using the CXL memory was quite high. So that more efficiently used the GPU compared to the solid state drive. And then the CPU utilization was lower. So that allows you to use your server to run other tasks. When the model was stored on the solid state drive, the CPU is quite active because it's essentially managing memory buffers. So all in all, decode throughput about 2.5 times better using the CXL memory. So that's important. You can get your news text summarization much faster. So in summary, the CXL memory offloading is beneficial. So we studied the large language model inference. It also allows you to use lower cost memory that's disaggregated from your server. Similar performance compared to pure system memory, as the chart showed, it was about, the performance is about 75% compared to pure system memory. So it's in this same order of magnitude. Obviously, you could try to store your memory model local, and this was small enough that you could. But as the models get larger and larger, that's not always possible. 2.4x performance advantage compared to solid state drive, and a 1.9x TCO improvement. So now let's take a look at the products. So here are the Photowave form factors. First off, we have a low profile PCI card that will fit into just about any PCI slot. The card supports by Gen 5 by 16, and it also supports bifurcation down to by 8, by 4, or by 2. We also have the OCP 3.0 NIC card form factor shown here. So you can purchase it as a NIC card. It's a little bit more compact than the PCI card. And we also have the active optical cables. So we have in development a CDFP and QSFP-DD. And we're also, seeing other requests, as more customers come online. So the latency, let's talk about latency a little bit. So there is on the cards, because they are connected to the motherboard, there's a retiming function. So their latency is, under 20 nanoseconds, end to end, so roughly, under 10 for each card. And that is with these retimers operating in CXL low latency mode. That is compared to the active optical cable, which does not have a retiming function of less than, so the cable's latency is less than 1 nanosecond plus time of flight. So with the active optical cable, you'll be dominated by, the latency will be dominated by the speed of light, right? Which is roughly, 5 nanoseconds per meter. That's all I have for today. So if you have questions, please put them in the chat. Otherwise, you can email info@lightelligence.ai.